Good afternoon, everyone. My name is Amjad Diab. I'm a second-year PhD student at the University of Texas at Austin. Under the supervision of Dr. Anka Furke, I've been exploring the intersection of machine learning and nonlinear finite element analysis. Today, we are glad to share with you our recent updates from our ongoing research. We will start with a general overview on UHPC. Then we will present on our proposed modeling approach and how we validated our proposed model. And then we will end with conclusions from our study and proposals for future research. Let's begin with the fundamental definition of ultra-high performance concrete, or UHPC for short. UHPC is characterized by a discontinuous pore structure and a relatively high percentage of fiber reinforcement. This makes this material stand out compared to other cementitious materials by having an ultra-high compressive strength and high tensile strength and tensile ductility, in addition to optimized durability and self-consolidating workability. These characteristics set UHPC apart as a material that's not just enhancing our current engineering applications, but it's also paving the way for innovations in constructions and design. Recent years have seen a surge in the application of UHPC, from innovative beam sections such as the pi girder, which was implemented in the Massachusetts Institute of Technology, to its uses in power plants, offshore structures, segmental bridges, girders, and columns. This called for the need to develop an accurate framework to analyze the response of UHPC members in order to fully utilize its potential in different structural applications. So, our modeling approach utilized Vector 2, which is a nonlinear finite element analysis software, which uses a smeared hybrid rotating crack model. Our compatibility requirements allows for bridged body slip along the crack. Our equilibrium conditions assesses both the stresses, average stresses in the, along the elements continuum, and the local stresses at the locations of the crack. In addition to that, we had specific constitutive relations to account for the optimized behavior of UHPC, including the artificial neural networks based tension model, which we will discuss about later in this presentation. Our modeling approach utilizes a two-dimensional finite element model, as shown here. The shown beam was simulated using plane stress element for concrete and discrete truss elements for the steel reinforcement. And we modeled the cracked concrete as an orthotropic material with an orthogonal stiffness matrix, which was constructed from the secant moduli, which is calculated based on the previously mentioned constitutive relations. Previous studies showed us that the tension model was one of the most viral models in simulating the response of UHPC members. However, the challenge associated with modeling this tension behavior arises with its high variation due to the large number of factors that influence this behavior, including the mixed design constituents, the curing conditions, or even the type of testing that we have employed. As we can see here, the results can change if we have a direct tension test or a bending tension test. So that left us with two challenges. The first one being, which tension test is the best to represent the tension state of UHPC elements in UHPC members, and how to model this response. We found out from previous experimental studies that the direct tension test is the most accurate test to represent the tensile state in UHPC members. So we started looking at the factors which influence this direct tension behavior of UHPC. And we found several factors, including the supplementary cementitious materials ratio to the concrete, to the used cement, water-cement ratio, superplasticizer-cement ratio, fiber reinforcement properties, including the propylene fibers, or PE for short. So considering the large number of factors affecting the direct tension behavior of UHPC, we opted to use machine learning in our approach to build the constitutive tension model for UHPC. So we started with constructing a database. Our database contained 575 experimental direct tension data points. We split our data points into training and testing sub-databases, and we eliminated the randomness in the splitting process to eliminate the possibility of data leakage in the learning phase. So the first model we implemented for the machine learning was the regression decision trees. The RDT for short worked by splitting the data into subsets based on the values of the input variables, effectively learning from the provided data, such as shown from the simplified example tree here on the right. The process starts at the root of the tree and divides the data as shown, data down its branches based on decision points, and makes the regression accordingly, as we can see here on the figure on the left. However, too much branching depth can lead to overfitting, as we can see in the case where we have a maximum depth of 5 in the figure. So we did parameter tuning for our developed regression decision tree by changing the maximum depth and the minimum number of leaves required to make a new depth. And we've reached a minimum testing mean square error of 7 megapascal, which we consider too high of prediction for the direct tension test. So we had to move along to the next machine learning model. The next model we looked at was the genetic algorithm, which generates a random number of possible solutions for a given problem. So as you can see here, we can So as you can see here, we have the number of possible solutions on the top left here. So, and it selects the possible solutions with the lowest regression accuracy. And as we can see here on the right, from the symbolic regression, and it performs a type of crossover in an effort to increase the accuracy of the regression process. And at the same time, the genetic algorithm also implements a mutation so that we don't fall into a local minimum. The genetic algorithm does this over several iterations, which we'll call here generations, in order to achieve the optimal solution, as we can see here. So we did the same thing with the genetic algorithm. We did parameter tuning for the number of generations or iterations and the population size, or the possible number of solutions. And we achieved optimal results, MSC, for testing mean square error of 4.6, which we still consider too high for our regression process. The third approach we looked into included the artificial neural network. The artificial neural network, or ANN for short, is composed of interconnected units or nodes called neurons, which are organized into layers, the input layer, and the one or more hidden layers, which are they are connected to the output layers. The hidden layers are connected of neurons, which are also connected using hidden weights and biases, which conform our activation functions. In this study, 2 hidden layers were selected for the prediction process for the direct tension characteristics. The network's output is compared to the desired outcome, and the error, which we call here the cost function, is calculated. The error is then propagated back in the back propagation phase in order to enhance our weights and biases in the network by calculating the slope of the cost function in an iterative process in order to reach to an optimal solution. This cost function here, where we can see the symbols y and yi, can change. For our case, it was a data-driven cost function, but it can also be a physics-based cost function where the y can be from the physics equation, or mechanics-based artificial neural networks where the y can be based on a mechanics model or any other model. So at the same thing, we did a parameter tuner for our artificial neural networks by changing the number of neurons in the first and the second hidden layer, and by changing the activation function. We used ReLU, TANH, and sigmoid activation functions. We can see that changing the neurons in the second layer had a better effect in reducing the mean square error compared to changing the neurons in the first hidden layer. We also changed number of epochs and the number of learning rates, and we achieved a minimum square error for direct attention test of 1.7 megapascal, which we considered acceptable to moving forward in our modeling approach. We can here see the results for the cracking stress, the ultimate tensile strength, and the strain at peak tensile strength with reasonably accurate R-square values. Given the black box calculation procedure of ANN, this called for the implementation of an approach to help explain how the artificial neural networks performs its calculation. So here in our approach, we can see how herein presented the Shapley additive explanations, or SHAP for short, and it helps us explain how the neural networks performed its calculation. So for our regression process for direct attention, the peak tensile stress, we can see that the fiber reinforcement percentages had the highest impact on the regression process. So we can see that in the feature value, we have the fiber reinforcement percentages up there have the highest positive effect, followed by the water-to-cement ratio, which have a negative effect, because as we increase the water-cement ratio, the direct tensile capacity decreases, which is reasonable, and vice versa for the superplasticizer, because as we increase superplasticizer, we decrease the water-cement ratio. So that helped us learn how our ANN is performing its calculations. Apart from defining our tension response based on the artificial neural network predictions, we also developed a compression softening model suited for UHPC with fiber reinforcement, which was based on experimental studies on UHPC panels under biaxial tension compression stresses. So what this compression softening model does is that it decreases the compressive strength of UHPC elements under transverse tensile strains. So now for our model validation, we started off with UHPC panels, which were tested at the University of Toronto. The experimental program was designed to study the influence of different levels of in-plane conventional reinforcement on the pure shear behavior of UHPC panels. We can see here how we did our model first. We did a model with a singular element with boundary conditions that simulate the pure shear behavior of UHPC panels. And we can see that our model performed reasonably accurate in modeling the response of the UHPC elements. The second phase of our modeling, we moved to modeling the response of UHPC beams that provided direct tension response of the UHPC incorporated in those beams. So we can see here that our model also performed reasonably well in modeling the response of these beams, which made us comfortable to moving to our third and last stage, where we model beams that did not provide the direct tension test results. Here we can see the UHPC beams tested by eConstruct with incorporation with the Pre-Stressed Precast Concrete Institute, PCI for short, which focused on changing the web thickness and the level of pre-stressing in the UHPC beams. And as we said, we we took the tension response from our developed artificial neural network, and as you can see, the model performed reasonably well in modeling the response of these UHPC beams. So, in conclusion, we concluded that the ANN-based model developed for predicting tension response, which is proved to be reasonably accurate to the set of the specimens analyzed, and it is feasible to employ an ANN-based tension response model for UHPC within a nonlinear finite element framework. For here, the direct tension database is available for whoever is interested. And our future work involves development of a Bayesian neural networks to account for the uncertainty in the prediction process, for including the curing conditions, fiber orientation, or even the strain rate applied to the beam during testing. We are going to use the developed formulation to analyze the response of retrofitted columns using UHPC and analyzing the UHPC shear walls in cooperation with University of Houston. And that's all we have. Thank you so much.